Right, just remember everything I said, because I didn't start recording. All right, so let's prove that all cats are the same color, which of course we know is not true. So let P of n be the proposition if there are n cats in a room, they are all the same color. All right, base case, P of 1. Got a room, there's one cat inside. Are all the cats in the room the same color? Yes. They might be gray, they might be orange, but P of 1 is definitely true. Okay, so now let's assume P of n. And let's prove P of n plus 1. So given n plus 1 cats, and I'll call these cats C1, C2, C3, up through Cn plus 1. Well, if I look at these first n cats, we're assuming P of n is true. There's a group of n cats in the room. These cats must all be the same color. And if I look at these cats, that's another group of n cats in the room. P of n tells me they must all be the same color. And cat 2, for example, must be the same color as cat n plus 1, but cat 2 must also be the same color as cat 1, and cat n and cat 3, and so all of these cats are exactly the same color. So all of C1, C2 are the same color. Therefore P of n plus 1, therefore P of n for all n greater than or equal to 1. So all cats are the same color. And you were mistaken if you thought otherwise. So what's wrong here?
Well, that C of 1, C of 2, C of 3 is a bit of junk logic.
Why?
Because every cat is a unique thing. You're assuming all cats are the same thing.
I'm not. I'm only assuming that n cats are the same.
Yes, but it's not any n cats.
Yeah.
That's the first thing.
P of n says any n cats. Right? If there are n cats in a room, they're the same color. But we don't have to have it be true. All we have to show is that if we assume this, we can prove that. Right? So what we've actually shown is P of n implies P of n plus 1. And that's the inductive step that we need to apply mathematical induction. So maybe all cats are the same color. Maybe we just never noticed. Maybe there's no light in that room, yeah. Maybe cats just use their mind control to like make us see different colors.
The entire population was colorblind?
Yeah. So where did we go wrong? Where did I go wrong? Say again? You only need one base case.
Did you choose poorly as the base case?
I did something poorly. You're on the right track.
Was it because your first assumption was false?
What was my first assumption?
That all the cats are the same color?
I never assumed that. I mean, I assumed P of n, right? But we always assume P of n. We assume the sum of 1 through n is n times n minus 1 divided by 2.
Assume that if you added a cat, that would be the same color.
I did not make that assumption. I just added a Cn plus 1.
Did you write
But I show that it's the same color as these because this is a collection of n cats. And we're assuming P of n. What? Maybe they're all the same cats, yeah.
Can you reword your proposition?
What would you like to reword it as?
Exactly n cats in the room.
I'm gonna say if there's n plus 1 cats, I can just remove one of the cats, and now I've got n cats in the room. And bringing that extra cat back in should not change their color. Although I guess we should question that if we're questioning any of this. We could probably redefine a whole new physics based on that property of cats. So it's fairly subtle here.
P of 1, you probably should have your base case be P of 2.
Why?
Well, because P of 1, it would be like saying Darwin, it would be like proving what was the other thing? The one that you did 2 of.
But we've done this all the time, right? When we show that the sum of consecutive integers is n times n plus 1 over 2, we said P of 1 says 1 is equal to 1 times 2 over 2. Right? And it's kind of reductive. We're just adding one integer, but that's still valid.
This P of 1 is like saying 0 times 2 equals 0.
Yeah, if that's...
It's essentially a 0 in this situation, in which case you're like, it's negative, and it would be like saying, okay, anything times n plus whatever.
That's not really a problem, though. If you can get from n to n plus 1, you can use a base case where it's just 0. That's actually still valid. But you're in the right area.
Did you start with P of n or P of n plus 1?
I started with P of n, so I'm assuming n cats are the same color.
So you change your basis during your proposition?
Changing my which?
Your basis of P of n.
P of n is always a statement about n cats,
Yeah,
right? And then I said, let's take n plus 1 cats. Well, there's a group of n, so they're the same color. There's another group of n, they're the same color, so they must all be the same color.
no, during this, you change your basis.
How am I changing it?
The basis only include n cats.
Includes n cats, yeah. So there's n cats.
You're
Problem is it's
excluding
a
one of the
specific set
cats.
of n
I can exclude a cat. I can take the cat out of the room and have n cats in the room.
That's still proving P of n, not P of n plus 1.
But then I bring this cat back in and I take out the first cat, and I show that these cats are all the same color.
You can't prove P of n plus 1 if you take one cat out and put one cat in. You basically prove P of n.
I've proved P of n on here and P of n on here, but if these cats are all the same color, and if these cats are all the same color, they must all be the same color.
Is
Not
the
true.
proposition saying that all n cats are the same color, or all the
Mhm.
cats in the room are the same color?
All n cats.
Okay.
So the n plus
So-
1.
So, well, where are you getting the conclusion that
N plus one cat
is the same color as C2, all of these?
Because there's a collection of n cats.
Is that a fallacy?
No?
It really feels like a logical fallacy.
But where?
Well,
Pn says I can take any n
Cat is
cats in the room, they're all going to be the same
cat.
color.
Each cat is unique, different cat.
Yeah.
And an n cats is referring to the specific first n cats that you put into the room. The
Right.
n plus 1 cat is not part of that collection. So if you move C1, n plus 1 is still not part of that collection.
But Pn, if there are any n cats.
Well, now you're changing your.
Well, it doesn't change my argument at all, though.
The first one.
That doesn't change the argument at
It
all.
didn't say the first n cats to begin with.
Yeah.
It just said n cats.
Yeah. I mean, cats aren't ordered anyway,
Apparently they're not colored either.
and they're not colored.
So,
This could go on forever.
Well, I think Connor got closest to it, but you're all pretty close to it right now.
And not having counts.
N is finite.
I have -1 cats in it.
Can't have -1 cats. Not that I know of.
yeah, actually, two different.
Okay, so let's look at my inductive step here. What exactly did I do here? I said, take the first n cats, those are the same color as each other. Take those n cats, those are all the same color as each other. Therefore, all of these cats must be the same color. I haven't proven that. And in fact, that's hard to prove. But it looks reasonable at first glance because, right, since these cats are the same color, in particular C2 through Cn are the same color, and since these cats are the same color, C2 through Cn are the same color, Cn plus 1 must also be that color, which means all these cats are the same color.
Two different sides.
But
Are C2 through Cn two colors?
no, they can't be two colors at the same time.
Okay.
Yeah.
But
Darn.
let's take a look at this. Let's apply this inductive step and try to go from P of 1 to P of 2. We know P of 1 is true. Let's see if this argument works to get from P of 1 to P of 2. Take two cats, C1, C2. Well, here's one cat, so that cat's the same color. Here's a second cat. That cat's the same color. Therefore, both cats must be the same color. No, doesn't work. Right? I'm assuming there's an overlap here. And there is, except in the case where n is equal to 2. If you've only got two cats, there's no overlap, and that argument falls apart.
You just start from 3.
If you could start from 3, if you could start even from 2, we'd be done. If we could show that any two cats are the same color, this proof is perfectly valid. Because take 100 cats, well, these two are the same color, so those two are the same, so those two are the same, and you work your way up, and you've got all 100 cats the same color. The base case we used here is a valid base case in itself, but this argument, this inductive step, does not work in going from that base case to the next case. So if I was good, this assumes that n is at least 2, and I haven't actually proven P of 2. So Pn implies P of n plus 1 for all n bigger than or equal to 2. That's absolutely true. That's what we just showed. And we also showed that P of 1 is true. There's no arguing with that. But we can't put these two things together and show P of n for all n. Right? That's not mathematical induction. Because our inductive step needs a base case that we haven't proven. So that's a really kind of subtle demonstration of where you need to be a little careful sometimes with what the values of n are. We just proved all cats are the same color. And then we proved that they're not. So. All right, so that's quirky. Also not going to appear on an exam. All right, other questions on that? Comments? All right, game time. So let's play a game. I used to do this with cut out circles from Domino's pizza boxes, and one of my students gave me this. He said, use this. All right, so this is called Towers of Hanoi. And it's a very old game with some history behind it. So here's the basic setup. We have three pillars here, and we have some discs sitting on one of these pillars. And these discs have different sizes to them. So let's just look at three of these. So we've got a small, a medium, and a large. And we're going to begin this game by putting all of these discs on one post. So I'm just going to start over here on the left. And that's how these things are stacked. All right, so we have the following rules for playing this game. This is Towers of Hanoi. So rule 1, smaller discs are on top of larger ones. Two, you can move one disk at a time. Three, you can only take the top disk. And four, you can only place on top of a stack. And your goal is to move the disks from one stick to another, right? So here's our 3 sticks, and we want to move from, say, this post over to this post. Let's see if I can. Yeah, that's a little better. All right, so we want to move from this post to this post. So we can move one stick at a time, one post disk at a time. We can only put small disks on top of bigger disks. We can only take from the top, and we can only put onto the top. So if I'm going to move this over here, right, I could put that there. I'm not allowed to put this disk over here. And I'm not allowed to somehow magically pick up this disk and move it over. And I'm not allowed to, put this disk underneath a bigger disk. Okay? But within these rules, right, the goal is to move your disks from one pile to another. So who wants to try to solve this? All right, come on up.
All right, just go ahead and do it then.
Yeah, just go ahead and do it. All right, cool. Good job. All right, so you've done this before, right?
Yes.
Okay. Okay, so that took 7 moves, okay, to move 3 disks. So suppose we throw a 4th disk in. Suppose we throw a 5th disk in. So if you have not done this before, do you think you could do it? It takes some trial and error, but it's doable. But let's be lazy. So he just solved this for 3, and if I start with 3 over here, you can still solve it, right? And if I asked you to put them over here or over there, you could still solve it, right? Okay, so there's our 3-disk solver, right? And now someone comes to me and says, hey, I would like you to solve the 4-disk problem. I want you to move from this post to the middle post. Well, being lazy, here's what I'm going to do. I'm going to call him up and I'm going to say, can you move these 3 disks to this post for me? And he'll say, yeah, he knows how to do the 3-disk problem. So he'll go bang, 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 and he'll move these over here. And we're going to ignore this big disk down here. Now this big disk is on bottom, so it doesn't stop anything from being placed on top of it, right? And we're never going to move this disk. So this is the same problem that he just solved, right? He's moving 3 disks from here over to here. And then I'm going to take this big disk and I'm going to put it onto our target post. And then I'm going to say, hey, can you do that again for me? Can you move these 3 disks over to here? And he knows how to solve the 3-disk problem. So he's going to go move, 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 move. And put those 3 disks over there, and I just solved the 4-disk problem. Now someone comes along and says, okay, well that was 4, but I bet you can't do 5 disks. Well, what do? You say, hey Nick, can you move these 4 disks from here to here? And I'll say, sure. And I'll make my moves and move those over. And then you'll take this and move it here. And then you'll say, hey Nick, can you move those 4 disks from here to here? And I'll say, sure. And I'll move those 4 disks over to here. And you just solve the 5-disk problem. But how did I do that 4-disk move? How did I move my 4 disks from here to here? Well, I used him to help me, right? So first I put these over here, right? So I got him to do that for me. And then I moved this. And then I said, can you move those 3 over there? And he said, sure, and he moved those over. And we solved the 5-disk. Can we do that for 6 disks? Sure. 7, 8. So how many moves does it take to relocate n disks? So theorem, moving n disks takes 2 to the n minus 1 moves. And we saw that he moved 3 disks and it took 7 moves if you were counting. 2 to the 3rd minus 1. And if you play this game with only 2 disks, and we want to move, say, from here to another post, we can do 1, 2, 3. So n is equal to 2, it took 2 to the 2 minus 1, that's 3. And if n is equal to 1, and you just want to move from one post to another, it takes exactly 1 move. So P of n is the proposition moving n disks takes 2 to the n minus 1 moves. So P of 1 says we can move 1 disk in a single move. That's clearly true. Right, so P of 1 is true. So let's assume P of n. So we assume that we can move n disks in 2 to the n minus 1 moves. Well, given n plus 1 disks, how do we solve this puzzle? First, we move the top n disks to one of the posts, and that leaves the largest disk exposed. We move that to our destination post, and then we move those n disks that we moved in the first place on top of that largest disk. So given n plus 1 disks, move n disks, move 1 disk, move n disks. All right, so take the top n and move those out of the way, then move the biggest disk, and then take those top n and move them on top of the biggest. Well, P of n says that to move n disks takes 2 to the n minus 1 moves. We know that to move 1 disk takes 1 move, and to move those n disks again takes 2 to the n minus 1 moves. So the total number of moves to move n plus 1 disks is 2 to the n minus 1 plus 1 plus 2 to the n minus 1, which is 2 times 2 to the n minus 1 plus 1 minus 1 is minus 1. And 2 times 2 to the n is 2 to the n plus 1 minus 1 moves. So assuming P of n, we've shown we can move n plus 1 disks in 2 to the n plus 1 minus 1 moves, which means we've just shown P of n plus 1 is true. And so by mathematical induction, P of n is true for all n bigger than or equal to 1. But this part of the proof is actually the key to how to actually solve this puzzle. Right? Move n disks, move 1 disk, move n disks. So 8 disks, how many moves does it take to solve the puzzle. It's a 250 pop quiz. $255. So 2 to the 8th minus 1. So that's not too bad. It'll take you a few minutes if you don't make mistakes. So there's a legend that there's a cave where a group of monks are playing this game with 64 discs. I think the discs are made of jade or something appropriate. And they're moving 64 discs from one pillar to another. And the legend is that when they finish moving all 64 discs, the universe blinks out of existence. So they're kind of counting down the existence of the universe. So are we in danger? Is that going to happen anytime soon? So what's 2 to the 64th minus 1? It's a pretty big number. Right, so if they move one disk a second, it's going to take that many hours, that many days, right, that many years. So we're probably not in danger.
Oh, they started centuries ago.
They started centuries ago, so we got a little less time than this. Okay, so this is a problem that grows really, really viciously in terms of complexity. 64 is not a big number, right? But 2 to the 64th is really huge. In 222, when we start talking about things like sorts and searches, we'll find algorithms whose complexity grows in the same way that Tower of Hanoi grows. And it's the reason why those algorithms will be so undesirable. Because 64 is a pretty small number. If it's going to take you like a quadrillion years to solve a problem, that's probably not a really great algorithm. Well, we can code this up. So let's take this approach and make a function called tower that solves Towers of Hanoi. So tower is going to take 4 arguments. It's going to take the number of disks you have, 4. It's going to take the peg that the disks are starting on, the peg you're trying to transfer to, and then I'm also being kind and putting in the third argument, which is the unused post. So I'm moving from post 1 to post 2, and I've got post 3 available. And tower is going to print out the solution to that. And I'm using an evil global to keep track of the number of moves that it takes. So, so this is the whole function. So I bump up the number of moves just to keep track of that. And if I only have one disk, I'm just going to move it from whatever the from post is to whatever the to post is. So I call my arguments from, to, and open, right? And I'm trying to move num disks from to 2, and open is available. So if num disks is 1, just move from the from disk to the open disk, or the target disk, and you're done. Otherwise, we do those 3 steps that we had here in the middle of our proof, right? First we move num minus 1 disks from the from post to the open post, and then we move 1 disk, which will be the biggest one, from the from to the to, and then we move the num minus 1 disks from the open post to the to post. And we do those moves, that first and third set of moves, by calling our tower function, because our tower function knows how to move disks, right? And the reason we know that this function works is by proving it inductively, right? How do we prove that this function works? Well, first we need to show that it works for a base case. If num equals 1, does this work? Yes, it does, because I can analyze this section of code and say, yep, if I've only got 1 disk, that'll move from the source post to the destination post. So my proposition, P of n, is that this function works for n disks. P of 1, we just proved that, right? That's this code right here. So now let's assume this works for n minus 1 disks. and see if it works for n. Well, if it works for n minus 1 disks, then this piece of code is going to do the right thing, and this piece of code is going to do the right thing, and this is just moving one disk from one post to another. And if we analyze our logic when we came up with this proof, these 3 steps will successfully move n disks. So as long as we know that this works for n minus 1, this algorithm works for n. That's how we prove this function is successful. That's how we prove it's correct. And move is just a print function. It just prints out what we're moving from and what we're moving to, and it puts out a new line every 5 prints so that it doesn't fly off the screen, right? So we almost haven't done anything, right? But we have a complete solution to this puzzle. Along with lots of warnings when we compile, but ignore those. Oh, I got rid of them. Okay, so towers, there's our solution. So let's try that. All right, so this one you just kind of have to watch. So move from post 1 to post 3. Move from post 1 to post 2. Move from 3 to 2. Move from 1 to 3. Move from 2 to 1. On the second line now, move from 2 to 3. Move from 1 to 3. And you can see we just solved a subproblem. Move from 1 to 2. Move from 3 to 2. Move from 3 to 1. Now we're down on the third line. Move from 2 to 1. Move from 3 to 2. Move from 1 to 2. 1 to 3. And then 1 to 2. And then 3 to 2. Hey, it worked. And it confirms it took 15 calls. So can we do this for 64 disks? There you go. Go to it. So that's solving the 64 disk problem.
How many steps per second is it doing?
Not enough. If I don't print, it'll go a lot quicker. But it's not going to come close to finishing. But if you were to follow those steps, right, this would be doing it. So this is a cool SLP, build a robot arm that does the towers. And this is not particularly memory intensive. There's no trick here. This is not going to blow up at some point. It's just a ridiculous number of steps, right? But it's not like it has to chew up billions of chunks of memory or anything. But we'll stop it just in case. So we're going to encounter the idea of induction a lot. It's going to keep coming up in different forms, right? And you may finish this course with an A and still not really have a good feeling about what induction is. That's okay. Okay. The reason that we teach induction in 215 is because it's going to help with what comes down the road in 222 and 223, right? So it takes a while to sort of settle into one's brain usually, but we'll encounter it multiple times in here. Anytime that you see something and it seems to be generalizable, and you can sort of see how to generalize from one step to the next, right? And you want to know, can we do this for all possible cases, right? There's a good chance induction is probably the answer. And it pops up in computer science for that reason. All right, did everybody turn in their homework? So let's run through the homework really quickly. So let P of n be the proposition. Oh, thanks. Okay, let Pn be the proposition that that sum on the left, increasing integers times increasing powers of 2, equals n minus 1 times 2 to the n plus 1. And as usual, if we look at what P of n plus 1 is saying, right, it's the following. Right, it's saying that that thing should be equal to n times 2 to the n plus 1. Is that minus 1 at the end? Plus 1, I swore it was a minus 1. Okay, plus 1. All right, so P of n plus 1 is basically saying take the left side, but also add n plus 1 times 2 to the n, and then that should be equal to n times 2 to the quantity n plus 1 plus 1. And then you start to look for how can we somehow do equal things on both sides of this, which we know is true, and somehow get to this. And sort of the simplest first stab is, well, this is the same as this. So what if we were to just add one more thing? Just add that new term. So if we add that to both sides, then we still have a true statement. So we're going to add n plus 1 times 2 to the n. And that's going to be equal to this right side, which is n minus 1, 2 to the n plus 1, plus n plus 1 times 2 to the n. And all we've done is add this on the left side and on the right side. So now we've shown that this is equal to that, and this matches the left side of Pn plus 1. So if we could somehow turn this right side into the right side of Pn plus 1, we're done, right? Then we've shown that this is equal to that, and that's Pn plus 1. So let's work on this. And maybe the easiest way to do this is just multiply things out. This is n times 2 to the n, minus 1 times 2 to the n, plus 1, plus n times 2 to the n, plus 2 to the n. And then combine. Well, there's an n times 2 to the n, there's an n times 2 to the n, so this is 2n 2 to the n. There's minus 2 to the n, there's plus 2 to the n, those cancel, and there's our plus 1. And 2 times n times 2 to the n, I can write that as n times 2 to the n. And there's my plus 1. And what is 2 times 2 to the n? right? Exponents. And there's our plus 1. And now I peek at my ignore section and I say, hey, that's the right-hand side of Pn plus 1. This was the left-hand side of Pn plus 1. That's what I started from. And so now I can say Pn plus 1 is true. So starting with P of n, we showed P of n plus 1. You have to show a base case. So you can show P of 1, and that's straightforward. And then you say by mathematical induction. Does that make sense?
Yes, I got that right. Confident.
You what?
I got that right. Confident out. Then finally, let's see if you do
At least you didn't erase though, right?
the next one.
Okay. I'll look through the X. Don't ever erase. Almost always when you erase something, it turns out to be the right answer. It's just one of those isms. I don't know where I put your homework. I may not have it. Yes, I do. There we go. Let's see. So that was question 1. Let's look at question 8.
Did you do question 8?
No.
Okay.
No, so last time at the board I gave you the choice of doing either question 8 or question 3. So let's just take a look at this. So prove that 8 divides n squared minus 1 for any odd number n using induction. We can do this with modular arithmetic pretty easily, I think. But let's do it using induction. So let P of n be the proposition 8 divides n squared minus 1. So P of 1 says 8 divides 1 squared minus 1, which is 0. Does 8 divide 0? Yeah, 0 is 8 times 0. So this is true. So now we want to prove P of n implies P of n plus 2, because we're only interested in odd n. So if we can prove this and we know P of 1, we can just apply this chain rule and say P of 3. And if we know P of 3 and we know this, we can chain rule and say therefore P of 5 and P of 7 and so on. Right? That's the inductive step. That's the generalization that we know how to do piece by piece. So suppose P of n, so 8 divides n squared minus 1. Well, I know P of n plus 2 is trying to talk about n plus 2 squared minus 1. We want to show that's divisible by 8. So let's just do some algebra. N plus 2 squared minus 1 equals n squared plus 4n plus 4 minus 1. So if 8 divides n squared minus 1, we can say n squared minus 1 equals 8 times, let's just say k1. So I'm going to take this expression and write it as n squared minus 1 plus 4n plus 4. And now n squared minus 1 I can write as 8 times k1 plus 4n plus 4. And n is an odd number, so I can write n equals 2 times some j plus 1. So this is equal to 8 times k1 plus 4n is going to be 4 times 2j plus 1 plus 4 equals 8 times k1 plus 8 times j plus 4, which is 8k1 plus 8j plus 8, which is equal to 8 times k1 plus j plus 1, which is equal to 8 times some integer k. And so 8 divides n squared, n plus 2 squared minus 1, and that's p of n plus 2. So how do you know to do this? Who knows? Right? Trial and error. Lots of error. Right? Trial and error, you make one more trial and you make errors. Yeah?
Oh, I'm just trying to.
Oh, you're
Sorry.
okay, no problem. So I kind of rushed it, but
Isn't 8 over 0 an invalid base case?
we're not dividing 8 by 0, we're dividing 0 by 8 and saying we get an integer. So this notation is confusing.
0 over 8 equals 0.
8 divides 0 means 8 divides 0, which also means 0 is divisible by 8, which also means 0 equals 8 times some constant that's an integer. So there exists a k, it's an integer such that 0 equals 8 times k. And there is a perfectly valid integer which makes that true, it's the integer 0. So 0 is actually divisible by every number, including 0. So the first time I did this, right, no idea that this was going to work. It's kind of desperation, right? You got to do something with p of n plus 2, which means showing that this is divisible by 8. So you expand it, and that n squared minus 1 just kind of screams out at you because you got to use p of n somehow usually. And that's p of n right there. Just take that n squared minus 1, write that as a multiple of 8. And then you're left kind of wondering, like, well, what am I going to do with this 4n plus 4? But throw in a few odd numbers and you'll see that those seem to be divisible by 8. 4 times 1 plus 4, 4 times 3 plus 4. And once you see that 4n plus 4 is probably divisible by 8, then you try to go about proving it using the fact that n is odd. So sometimes it's like, this is the only possible path that I know how to take, so I got to make it work. That's a lot of mathematics. So why does induction work? We've been doing this for over a week. We've been saying if you can prove p of 1 and you can prove p of n implies p of n plus 1, then you can say p of n for all n. But we haven't proven that statement. We haven't proven that mathematical induction is really a thing. It makes sense, hopefully at some level.
Use the chain rule proposition.
You can do that for a finite number of propositions, but again, how do we know that that will work up to p of 1 billion?
Mathematical induction.
So if we could use mathematical induction, we could use that to prove mathematical induction. But that's a slippery slope. Yeah, but I already had mathematical induction. But how do we know mathematical induction works? And that follows from a property. Given any set of positive integers, it can be an infinite set, but given any set of positive integers, there exists some integer in that set less than or equal to all the other integers. for example, if I pick my set to be 3, 5, 11, 23, 200, right? There's an integer that's less than or equal to all the other integers. That's the integer 3. If I pick my set of positive integers to be the set of prime numbers bigger than 100, then there's an integer, namely 101, that's less than or equal to all the other integers in that set. Okay, that's a really hard thing to prove. That gets into some really bizarre, scary set theory to try to prove that, and it breaks down into things like the axiom of choice and Zorn's lemma and stuff we don't want to talk about yet. But if we believe that this is true, and it's only true for positive integers, right? Because if we have negatives, we could have, you know, all the negative integers, and there's no integer that's smaller than every other. And if we have real numbers, I can take the set of all real numbers bigger than 0, and there's no real number that's smaller than every other real number in that set, right? Because I'm not including 0. So if you pick 0.0001, there's another number in that set that's even smaller than that. So this doesn't work with reals. It doesn't work if you throw in negatives. But for positive integers, there's always some integer that's smaller than or equal to every other number in that set.
Couldn't you just prove p of n minus 1 and work your way downwards?
Well, that's exactly what you use this for, right? So if you suppose that p of 1 is true, and you suppose that p of n implies p of n plus 1, but you suppose that p of k is false for some big number k, you can work your way down and show since p of k is false, p of k minus 1 must also be false. Otherwise, it would imply p of k. And if p of k minus 1 is also false, p of k minus 2 is also false. So you form a set of all the positive integers for which p of k is false. And you find the smallest element in that set. And there's two possibilities. That element could be equal to 1, but that would mean p of 1 was false, right? So that element must be bigger than 1, which means that p of that element is false, but the p of the smaller element, that element minus 1, must be true, because it's not in this set. And now you use this to say, well, if that's true, then p of k must be true. And so you can show that if p of k fails to be at some point, then one of these two statements must be false. So you use this well-ordering property to basically show that you would break one of these two things that you've said were true. And so your only conclusion is that there is no such p of k that fails to be true. And that proves induction. And that gets into some weird stuff. So that's a good stopping point for a Friday. So we can talk about questions related to this next week, but then we're going to go on and we're going to start a new topic on Monday, and that'll take us into some other aspects.
Well, there would be any kind of homework to do.